What is Runge-Kutta method?
Runge-Kutta method is a family of numerical method that uses an approximation for an ordinary differential equation. And who formulated this method?
This method formulated by two German mathematicians, Karl Runge and Martin Kutta.
Now, are you ready to learn this method? Now, I'm going to show you how Runge-Kutta method uses an approximation for an ordinary differential equation. So, this is our y sub 0 and this one is our x sub 0, and we go each far away. So this serves as x sub 0 plus h.
Sure.
And then we have our solution curve here. And then in Euler's method, he uses a tangent line to solve for a slope. So the intersection between the slope curve and the tangent line is just a function of sub-0 and function of y sub-0. Now, we have to evaluate the slope field of this point. So now, we already have our new height. This one is our new height. In Runge-Kutta method, this first point is our K1. And then we take the half size of this height and multiply it by our increment base, which is K1. So we have to project it here. And then we also take the half of this step size. So that intersection serves as our K2, which defines y sub 0 plus hk1 over 2 and x sub 0 plus h over 2. So now, our next step is to take the half size of this K2. So it's here. H over 2 and then multiplied by our K2 because this serves as our increment base. And then we have to project it again in line with our K2. So this point now is what we called our K3. And then we take the full height of this K3. Yes. And lastly, this is our K4. So this K3 is y sub 0 plus h K2 over 2. And then this one is our y sub 0 plus h over 2 and function of y sub 0 plus h K1 over 2. And then our K3 is here. The function of x sub 0 plus h over 2 and function of y sub 0 plus h K2 over 2. And we have our K4, which is the function of x sub 0 plus h and function of y sub 0 plus h, K3, multiply by K3. So now, we can have our general formula, which is, wait, I'm just going to erase this one. So our general formula is x sub n plus 1 equals to xn plus the step size over 6 multiplied by k1 plus 2k2 plus 2k3 and plus k4. Why do we have 6 here? Because we take the weighted average of these slopes. So we have here 1 plus 2 plus 2 and plus 1. That's why we have 6 here.
A few moments later.
Runge-Kutta method is a modified Euler's method. So we have this example, and we were going to use Runge-Kutta method for determining the approximate values of y when t is 0.2, 0.4, and 0.6. So before that, we need to find the step size, which is h is equal to delta x is equal to the final value minus the initial value over n. So our final value here is 0.6 minus the initial, which is 0, over our n is 3. And we will have an answer of 0. So this will be our h, or the step size. So before that, dy over dt is equal to y prime. And y prime here is 3t e raised to negative y. And here, our t here is 0 and our y is 2. t 0, y 2. So, in Runge-Kutta method, k1 is equal to function of x and y. So, f. And in this equation, x is also equal to t. So, x is equal to t and t is 0. And our y here is 2. So, we have these coordinates and we will going to substitute this to our equation, which is y prime is equal to 3t e negative y. 3, our t is 0, e negative y is equal to 2. And we will going to have an answer of 0. K2 is equal to function of x plus 1/2 of h and y plus the 1/2 of h and multiply the value of our k1. So let's substitute our x or t is equal to 0 plus 1/2 of h. Our h is 0.2 and our y is 2 plus 1/2 of the half step size and multiply the value of k1. And we will going to have a function of and we will going to have an answer and we will going to have a function of 0.1 and and 2. So again, we have a new coordinates and we will going to substitute this again to our y prime. So let's substitute. So 3, our t it will be 0.1 and e raised to our y here is 2 and we will going to have an answer of 0.04060059. So get at least 8 decimal places. And this will be our K2. And now we are ready to proceed with the K3. Which is equal to function of x plus 1/2 of h and y plus 1/2 of h and multiply the value of K2. So now let's substitute again. K3 is equal to function of our x is 0 plus 1/2 of our h, which is 0.2, and our y is 2 plus 1/2 of h, which is 0.2, and multiply the value of K2, which is 0.04060059. And we will going to have a value of 0.1 and 2.004060059. So I'm just going to erase this part. I'm just going to rewrite the values of our k here. So now we have the coordinates of K3, which is 0.1 and 2.004060059. And we will going to substitute this again to our y prime. So our t here is 0.1 e raised to, our y is 2.004060059. And we will get an answer of 0.040436078. So this will be our K3. So let's write it here. 0.436078. So let's proceed to K4. K4 is equal to function of x plus h and y plus h and multiply the value of K3. So let's substitute the values. Function of our x is, or t, 0 plus our h is 0.2 and our y is 2 plus h 0.2 and our K3 is 0.047436078. And K4 will be function of 0.2 and we will going to get an answer of 0.040436078. And we have again the coordinates of K4, which is 0.2 and 0.040436078. And we will going again to substitute these coordinates to this equation. So y prime is equal to 3t e negative y. So let's substitute. So 3 multiply the t. Our t here is 0.2 e negative y 0.04043678. And we will get an answer of 0.080054874. This will be our K4. So K4 is equal to 0.080548474. So now we are ready to proceed with finding the value of y when t is equal to 0.2. So the formula is yt plus 1 is equal to yt plus h over 6, multiply it by k1 plus 2k2 plus 2k3 plus k4. So our t plus 1 is 0.2 and our yt is equal to 2 plus our h is 0.2 over 6, and we will going to substitute the values of k here. So our k1 is 0 plus 2, k2 is 0.04060059 and plus 2. Our K3 is 0.0404360078 and plus our K4, which is 0.08054874. And we will going to have an answer of this 2.008087402. So it says here that when t is 0.2, our y is 2.008087402. So I will just going to put ilagay ko na dito ate. So now, in order to get the y when t is at 0.4, this will be act as our initial value. So I will just going to write this as y 0.2 is equal to 2.008087402. I'm just going to do the same procedure what I did earlier. So I'll show you how it works. So again, K1 is equal to function of x and y. So K1 is equal to, so K1 is equal to, so instead using this initial value, I will going to use this. So this will be 0.2 and our y will be 2.008087402. So these coordinates, we will going to substitute this to our y prime and repeat the process what I did earlier. So until you get the value of y when t is equal to 0.4. So repeat again the whole process what I did, and until you get the value of y when t is equal to 0.6. So you're going to stop here at 0.6 because we just need the values of y from 0 to up to 0.6.
So now, we already have the values of y using Runge-Kutta method or the approximation by Runge-Kutta method, and then we also have here the values of y using the Euler's method. And then, using the exact solution, we get the values of y here. So now, we're going to evaluate the errors between the two approximations. So this is the solution how to get the absolute value and the relative value. Absolute value is just you have to subtract the exact values of y from the approximation we have used. And then we have to get the relative error using this formula. Absolute value error over exact value and multiplied by 100. So, if we do this one, in Euler's method, we have this. And in our Runge-Kutta method, we also have this. So in this table, as you can see, the absolute error of Euler's method when time approaches at 0.2 is 0.00809 and its relative error is 0.4028. While in arcane method, the absolute error when time approaches at 0.2 is 1.24 times 10 raised to negative 7. And its relative error is 6.1750 times 10 raised to negative 6. While the error here in Euler's method when approaches at 0.6 is 0.02233999, while in arcane method, the error when time approaches at 0.6 is 7.7753 times 10 raised to negative 4. So as you can see, in arcane method, the error here is much lesser than the Euler's method.
And that's all about Runge-Kutta method. Thank you.